Hello, I'm Aki Hoshide.
And I'm Megan MacArthur.
We're astronauts living and working aboard the International Space Station. Have you ever wondered how astronauts orient themselves in space when there is no feeling of up or down? In this episode, we'll discuss the vestibular system and the effects of free fall on our sense of direction up here on Space Station. Let's go try out some experiments with spatial orientation. The vestibular system is the sensory system our brains use to process movement using the perceived pull of gravity, structures in our inner ears, and through processing visual cues from our eyes. This information is necessary for balance, motion, and spatial orientation. The vestibular system is made up of several parts primarily located in the inner ears in a series of interconnected chambers called the labyrinth. The labyrinth has 3 semicircular canals, each oriented in a different plane to detect different movements.
In the micro-G environment here on the space station, the pull of gravity our body is accustomed to is different, and the vestibular system receives mixed messages. The semicircular canals sense head rotation in space, just as they do on Earth. Because the otolith organs rely on gravity to detect linear motion, they don't function the same way in micro-G as they do on Earth.
You've probably experienced similar mixed messages on Earth. Some people feel dizzy when they read a book in a moving car. The structures in your ear pick up on the motion of the car, but your eyes are fixed on the motionless book. These mixed messages can cause dizziness as your brain tries to determine if you're at rest or in motion. We call that dizzy feeling motion sickness.
Docking sequence is complete. Welcome to the International Space Station.
Endurance copies and docking complete. I'm happy to be here at the ISS.
This is similar to the way many first-time astronauts feel when they arrive on the space station. Up here, we call that space adaptation syndrome, or space motion sickness. This is a period where our bodies are adjusting and orienting to the new free-fall environment. One way we fight off space motion sickness is by reducing our body movements until we are acclimated. We also use labels, signs, and the design of the station to help orient ourselves. Lights are positioned up along what we call the overhead, and air intakes are positioned down towards what we call the deck. When we return to Earth, our bodies once again must adapt to perceived change in gravity.
Close your eyes and think about where you are right now. Can you determine which way is up with your eyes closed? What about down? Now, open your eyes and think about what signals you receive to help you determine direction. On Earth, we perceive up or down relative to gravity. While in orbit on station, we're essentially in free fall. There isn't a true up. Up could be anywhere.
Welcome to Which Way Are You Pointing?, where our astronauts try to figure out their orientation while they're in micro-G. They'll have eye masks on and earplugs in to remove those senses. On the space station, gravity has mostly been removed as well. They'll pick an object and see if they can point to it after being spun around. First, some terms you should know. Pitch is shown as an exaggerated nod. Roll is shown as you move your head from shoulder to shoulder. And yaw is shown as if you were shaking your head no. Let's play.
Target, Lisa flag, rotation, pitch.
Wrong again, Mark. Okay, Shane, let's see how you do.
Target, laptop, rotation, roll.
There are just too many missing pieces of their vestibular systems to accurately orient themselves.
I encourage you to think about the way your vestibular system helps you respond to information from your environment, and take note of what's happening next time you feel a little off balance. Thanks for exploring the effects of micro-G on the vestibular system with us today. See you next time.